Hello, good evening. My name is Blake Walkowiak. I am a ocean and atmospheric science major here at UCSD. I actually have a minor in political science, and I currently am a research assistant at Scripps Institution of Oceanography. And today I want to present uh, on climate science and Python, mainly focused on the Pandas and Numpy libraries. And the meaning for this workshop isn't necessarily to try to, you know, push Python onto you, but kind of show the abilities that you can learn from data science and from Python and apply it to your physical science studies, research, or collaboration with colleagues and peers at UCSD and beyond into your future careers. So with that, this is the week 6 DS3 Calgo workshop on climate science and pandas. So why use Python? What are the intricacies that are going to be enable to you to be a productive data scientist, as well as physical scientist, engineer, astronomer, etc. So the uses of Python range from data science to finance to game development, mapping and geography and GIS software. And there's just a plethora of applications that you can use when it comes to Python. For me in particular, I have used the data science packages related to Pandas and Numpy specifically in my work and research at the Climate, Atmospheric Science and Physical Oceanography Department at Scripps Institution of Oceanography. So the Python ecosystem contains a mature and ever-evolving assemblage of computational tools for working scientists. And I would say that the working scientist language can be daunting in that you'd expect high-level researchers, whether it's at UCSD or MIT, Caltech, wherever in industry, for example, but it's actually really easy to understand. And first glance can be scary, as with in every programming language, but I think Python is especially readable, and you can implement the language into whatever research or work you're doing. The modules and libraries especially provide a vast opportunity for data-intensive research. Thousands of individual days, whether you're working with timescale data or physical properties having to do with physics, radiation, all kinds of great stuff can be utilized and analyzed in Python. And the open source initiative makes acquisition of these first step tools seamless. So the ability to just go on GitHub and see other researchers involved in your field, their work, and what they've done with Python can be kind of a next step in your own research, in your own avenue, right? So piggybacking off of that, one of the great libraries is Pandas. So we actually have an intro to Pandas workshop that we did last quarter in the fall of 2020, which has these introductory applications and functions, and teaches you the minute analysis using for loops, for example. And so it's a really good workshop if you want to check that out. So Pandas is useful in data analysis and manipulation, as I said, powerful in application, yet easily utilized, obviously through practice. I said that Python is pretty readable and easy to understand and apply, but obviously you need practice. And through this practice, you will end up finding some really cool and great insights into your own work, as well as the work of others. And it'll help you to understand basically the intricacies of computer software languages as it applies to your field. So when working with large data sets, Pandas can be a great tool. What about Numpy? So Numpy is another package or a Python library that allows you to do some really intricate computing with large arrays. So this quote actually sums it up really well. The de facto standard of array computing today. Numpy is vast and very easily utilized as well, I would say, but it allows for some opportunities that you wouldn't have otherwise. So this also provides a plethora of mathematical computation tools, whether you're trying to find the log of data, linear regression, let's see, all the avenues you could think of in calculus are kind of available with NumPy, as long as you obviously understand the material you're working with and how to apply these tools. So extremely fast with even larger, more complex data arrays are the tools available by given to you by NumPy. And so this image I pulled from MIT Computer Science is of the first image of the event horizon of a black hole. And basically, NumPy along with SciPy and Matplotlib enabled the scientists at MIT's Computer Science Department to develop this image by producing the data assemblage, which is of vast amounts of radiation data from the light that is being captured by this black hole and being pulled in, which is extraordinary to say the least. So the fact that you can implement these seemingly introductory libraries into such a complex analysis is really cool, and it just shows the infinite possibilities of using Python. So Jupyter Notebook. I just wanted to put out that Jupyter Notebook was my introduction to Python, as I think a lot of data science students or computer science students at UCSD interact with their first courses. And it's really great because it's an execution environment that supports Python programming, but other programming languages as well. And it really allows for ease of use, especially when visualizing data sets, manipulating data, cleaning your data and transformation, as well as performing numerical simulation and much more. And that's free to download open source as well online through Anaconda. All right, so heading into my case study that we're going to be discussing, and just an introduction. So here you can see this is actually my PI, my principal investigator, Amato Evan, at our field site, which is in the Sonoran Desert, or more locally known as Anza Borrego. And we get a lot of northerly dust storms which picks up dust and kind of drives itself. So it creates these huge dust plumes. And this is actually really analogous to a lot of desert regions around the world. And so in analyzing the data, you can get some really cool insights into how dust is interacting with the lower atmosphere, as well as how similar particulates will interact in similar desert regions. So here at Scripps, we are working in collaboration with NASA, and especially with a program called AeroNet, which is the Aerosol robotic network. You can see in this image, there's a tool called a simul-sun photometer, which wakes up, looks at the sun, and determines how much particulates, how dense these particulates are in the atmosphere, ranging from dust, ash, clouds, etc. And so what we want to do is establish an accurate classification algorithm for these suspended particles, basically determining whether we have dust in the atmosphere or clouds in the atmosphere, because this has huge implications for climate models. For example, there's a recent study that came out that says we only have accurate measurements of 50% of the suspended dust in the atmosphere at one time, which has huge implications for radiative forcing. So basically how much sun is getting down to the lower atmosphere, how much the land is absorbing it, which basically tells you how much the globe is warming, how the impacts of these particles on the physical properties of the atmosphere, and much more. So in general, science research relies on data acquisition and processing and the insights that you'll get from it to apply to these huge, groundbreaking research topics that hopefully many of you, or at least those of you in the audience, will be embarking on in the future. So dust or clouds, that is the most simple way I can express the research that I am doing, and what we're interested in at my lab. So this bottom left image is a GIF of, or GIF, however you want to say it, of we're using a IID round track camera. So this camera is looking directly east towards our field site. And as you can see on this one day in particular, it's about to start. So this is the morning 1500 UTC is actually going to be around 9 a.m. Pacific Standard Time. And throughout the day, the winds pick up because the Earth is heating up and warming, and that causes the advection of the suspended dust, which is interacting with the sunlight and with these clouds in the lower atmosphere. And as you can see in the image to the right, this is a backscatter plot actually created in MATLAB. So I did cheat a little bit, but it does pull some interesting implications for what's going on. So as you can see around 1900 UTC, there is this huge plume of suspended dust that is within the first 2 kilometers of the atmosphere. But the issue is we start to see this interaction around 2100, which is 2 p.m. of these cumuliform clouds in the atmosphere moving in. And the problem with this is that our device is determining that, misclassifying this dust signal as clouds, which has huge implications for climate modeling in the region. And obviously, as you could think, with the Sahara Desert, all these other regions around the world, if the same issue is occurring and is prevalent, could have major implications for understanding how dust is interacting with the atmosphere. So with those devices that I was showing you earlier, we can collect daily data on a plethora of variables that give us insight into the properties in this region. And so when you pull the data initially, you want to get to know it and you want to understand what the data is doing. So you basically spend some time understanding the data structure and the data types. So going back to our Intro to Pandas workshop we had last quarter, you can see some of these initial abilities of Pandas in determining, what the data you're working with looks like and how you can first take a stab at it to see what it's telling you. So make your data readable. Accessibility is a key feature in Python. So if you don't know Python, no worries. Once you get comfortable with it, you could take a look at the site again and see that this is just a function that works through the columns of your data frame and is basically telling it to remove these quotes, remove all this stuff that's going to be all these worthless pieces of text that we're not going to be able to use to understand our data in general. And so this is what we first get from Aeronet's site, right? A bunch of data, unorganized, unprocessed, basically telling us nothing, right? So how do you get and develop the data that you're going to use in understanding what's happening in any of your research, whether it's, like I said, physical science, atmospheric science, or beyond? So after calling that function, calling to take out January 29th, which is our day for our case study, we can organize this data in such a way that it's easily workable and can, take what we throw at it, right? And in visualizing this first data, you want to get an understanding of what you're working with. That's always the main idea, right? If you don't know exactly what's happening, how are you going to draw insights from it that can help you in, whatever research or research avenues you're trying to take, and whether it's solving your hypothesis or just answering simple questions like, okay, what is this variable even doing? So whether you're studying the physical properties of the atmosphere, radiation from a black hole's event horizon, or evaluation of a company's free cash flows, all of this can be convoluted. So these simple visualizations can be really helpful. Python is a great aid for taking that first look, as well as the final glance eventually when you're done with your experimental hypothesis and drawing conclusions. You can see exactly what you did and how it relates to your first initial visual and what was going on when you really took that first stab at your data. So attacking the problem efficiently, you may need to think again when you're doing your analysis, right? You can explore the available documentation and try to form a link between your data, subject, and language. And what I mean by that is you may have a bunch of data, right? And you may end up having data that you don't really need. You need to look through your data set, whether you have random variables or it's full of null values that are bombarding your data and are going to really impact your analysis, and you need to clean that out. And the ability of Python to do that is really important, because if you're trying to implement some sort of analysis or perform some sort of regression, for example, the dirty data, I guess, the quote unquote dirty data, can really impact your analysis. So it's really important to get an understanding of your data, and so that you can approach it in an efficient manner, so that you're not wasting your time and you're really using the most of what Python has to offer. So in this first plot, this is AOD at 500 nanometer wavelength. So basically AOD is aerosol optical depth. So going back to what I was saying before, this is telling you exactly how much particulates, I wouldn't say exactly, from a different point of view, basically, it's an atmospheric science variable telling you how much particulate is in the atmosphere. So as you can see, as the day goes on, progressing from 1500 UTC, which is around 9 a.m., just as in the backscatter plot and the GIF I showed you before, this huge plume occurs, and the atmosphere becomes filled with dust and particulates. And this AOD scale is actually from 0 to 1. So the fact that it reaches 0.6 is basically saying that there's no air above you, it's all dust, which is, you know, insane to say the least, and especially for someone who's studying atmospheric science, quite awesome. And then we decline into this cloud time around 2100 to 2200 UTC, which, if you look at the legend, you could see that I wrote AOD 500 nanometer trial, which is basically the level 1 data, and is data that AeroNet, which is the NASA process data, is showing us, which is saying, okay, let's identify that dust as clouds, right? So the problem is that a huge dust signal, which has crazy implications for what's going on in the atmosphere, is getting removed erroneously because NASA's algorithm is saying that it's cloud, is misclassifying dust as clouds. That's the basic premise. And so from this, we realize we need to construct new variables. And a lot of the time, this is what you're going to have to do, right? You're not going to be given everything you want from the data. It's not going to be handed to you on a silver platter. You need to figure out what's going on, how you're going to, from your approach and from your first, run through of your efficient analysis that you're going to be performing, what needs to happen, and then you take it on. So we decided we needed to create angstrom exponents, which is basically a variable that determines clouds from dust. It says the larger the particle, the smaller the value will be. So cloud droplets are, on the scale of particulates in the atmosphere, huge compared to dust. So we were able to build these super important properties based on the data we were given, right? It wasn't something that the variables weren't given to us. We had to construct them on our own. And that's going to be a huge process of any analysis you're going to be doing, whether it involves what I'm working on or any type of mathematical theory, as well as oceanographic science, economics for sure, macro, micro, either way, you're going to be required to understand how to make new variables, and from the insights that you gather before, create new insights that you can implement to further your understanding of the material you have at hand. So here's another example of something, a variable that we had to create basically from scratch because it wasn't given to us, right? Piggybacking off of what I just said, you have to perform the analysis as if you were the scientist that first structured the data set, right? You need to become efficient and become comfortable understanding how to build onto the data set, not just take insights from it, but build onto it and expand it yourself so that you have the available assets you need to become a better researcher and solve these complicated problems that everyone who is performing research or even in industry is going to have to tackle, right? So let me read you basically a summation of what we had to work with. I mean, there was definitely some more from a paper describing this algorithm that was misclassifying dust, but it says the slope of curvature M represents the average characterization of the solar aerial shape across a scattering angle, 3.2 to 6 degrees range, in which a large magnitude signifies the potential presence of large particles as curvature increases with increasing scattering angle across the forward scattering peak. I'm just going to say that is a very confusing sentence, and that is something that's very hard to grasp. But being able to having the insights that you do have from knowing the science behind whatever you're working with, you can apply this seemingly impossible sentence to a function that is going to return that simple value or slope of curvature variable, in this case, M. As you can see, we start with this function, which takes in num, which is actually a set of values, which returns a set of coefficients, which is the variable we wanted. And you were able to do that using Python and using Numpy and using all of these libraries that were given to you and using these if statements. And the abilities are just endless is what I'm getting at. These variables that you can build on your own can really help you take the next step in your career. So knowing Python is, I wouldn't say essential, but it is definitely something that will boost your resume, whether you're trying to get into a research lab or get into industry. If you're not a data science major, for sure, I definitely recommend taking a course in it. And you can, you'll then be able to approach the research you're working on from this nuanced point of view, which is really great. Now, oftentimes you find out these really great insights and you're performing this code in such a way that you're just rolling, right? But then sometimes you find out you fail. And this is where visualizations come in handy yet again. So we were attempting to replicate basically NASA's algorithm to figure out where this error in the misclassification was occurring. And an attempt to replicate someone else's work sometimes, and in our case, ended up fruitless. We didn't get where we wanted to go. As you could see in this AOD 500 nanometer comparison, we wanted our data, which was the AOD 500 nanometer trial, to match up perfectly with AOD 500 nanometer from AeroNet, right? So in the scatter plot, you could obviously see we had some discrepancies in our results, and we weren't able to figure out what exactly they were doing. And oftentimes you're not going to be able to. You'll email the collaborators, you'll try to understand what they were doing, you'll try to get into their head, but either you won't understand what they're trying to say, you won't understand what they're doing exactly because their paper isn't 100% in the detail that you were expecting. This is the same whether you're trying to take work from your higher ups, whether you're in industry, whether you're working as a data scientist or computer scientist, and they give you a problem to solve, and you just can't take their data and what they did and replicate it exactly. But there is kind of a greatness with that. You get to approach it from your own view and from your own knowledge and from what you take from the Python community and apply it to the data yourself to try and figure out a new way to approach things. And this is where huge, great insights in science come from. There are multiple avenues to approach a problem with Python, and it's quite unique in that aspect. So let's go ahead and see what happened. Getting into exploring Python more, there's a plethora of modeling libraries and modules built for modeling, in particular what we were trying to do. Advantageous to physical scientists, especially, are the machine learning packages, as well as whether you're trying to predict whether your goods will serve well on a certain market or sell well on a certain market and bring in profit you want, right? You want to teach the machine how to better inform your company or your research or the government, wherever you decide to work and wherever you're going to bring your intuition from. So in our case, specifically, I actually had to perform this in MATLAB as well, because some of the older researchers you'll find only know certain languages. And this will probably be the same case when the next coding language comes out and you're the only one who knows Python. So be prepared for that. Obviously, the world's forever changing, but we used scikit-learn's GPR package to create a dust restoration algorithm. So we decided not to take the same approach NASA did, but instead approach it from our own point of view and utilize the various applications Python has to offer. So I'm not going to dive too much into the machine learning aspect. We actually had a great workshop for DS3's machine learning workshop from week 5 by Yash Padar, and he is a great resource in a definite up and comer in DS3 for sure. So he has some awesome workshops, and I very much recommend you go check him out if you're interested in machine learning and getting to know more about exactly, what type of work is going on in this scene. So GPR is actually Gaussian process regression model, which takes a Bayesian approach to modeling. Basically, you're assigning probabilities to past data that you've acquired, and you'll be able to take new inputs and base those new inputs, the variables themselves, which we use the angstrom variables, as I mentioned before, and compare them against the probability distribution that you attained using this model. And the outputs will tell you whether you're seeing dust or clouds, or whether you're seeing a black hole or not. There's a universe of different insights you can gain from using machine learning, obviously. So our own results. So following the application of our dust restoration algorithm, we actually had a really positive result, 95% dust restoration over 20 sample days. So where these huge data plumes came from, we actually were able to analyze over 300 days of data, which in hindsight, doesn't seem that great. The more data you have, obviously, the more accurate your predictions will be, and the outcome of your journey. So a 22% false positive rate, which actually means that we were only classifying clouds as dust 2% of the time, which is exactly what AeroNet was doing, which is great that we were able to have such a prominent and excellent result. And as you can see, visualization comes in handy, as I was talking about previously. You get to take a last glance at your work. And in reality, it's not the last glance, right? You are going to be able to be informed about what you did and informed about your methodology, so that even if you don't have the best result that you can get, which obviously 100% is better than 95% in my case, you could always take it a next step further and use what you have. And through this visualization, create another more efficient method at solving the problem. And so obviously we can get to 100% restoration, hopefully maybe with the application of a more nuanced approach and particularly effective machine learning algorithm that involves a better suited way of solving these physical problems that we have seen at our Salton Sea site. So as you can see, our results are pretty similar to the in situ collection of backscatter data from LiDAR. LiDAR is basically sending lasers up into the atmosphere, and whatever it hits, it bounces back, and it tells you the speed at which it's doing so and the time at which it takes, and that tells you the height of the suspended particles in the atmosphere, which is pretty cool in and of itself. So overall, as you can see, positive result. Python came through for us again, and we're still in the process of implementing this algorithm at other dust regions around the world, and hopefully by accurately classifying these dust signals, we'll be able to understand climate models more and get that 50 to 75% of known dust in the atmosphere to 100%, so that we can better analyze and better understand the climate as it continues to change due to anthropogenic changes, as well as what we're beginning to see from nature itself, whether it's increased hurricanes, whether it's increased droughts, in particular those regions such as San Diego in the subtropical area of latitudinal areas of the planet. So it's not just insights that we're gaining into our one simple subject, but it's the application beyond that. It's moving towards into other subject areas where your research is benefiting more than just yourself. It's actually can end up benefiting insights that go to NASA, right? They'll take those insights, they'll share them with the government, right? The government can then produce legislation and policy that can end up benefiting you by giving you better grants and helping you in aiding in successfully succeeding in gathering those grant proposals. This is a bit off topic, but the fact I'm trying to get at is what you can do with Python can really be beneficial to the overall success of your field, and especially the research you're doing, and then have greater application to humanity as a whole, as I've just discussed with this simple, seemingly simple model of determining dust from clouds. So, in summary, feel free to check out this article to learn, to apply them, to understand them. You're not just going to get them the first time, but as you do study them and as you do become more familiar, the application is immense and really intriguing, right? So such models include scikit-learn, which is one that I was able to utilize, PyTorch, Pandas that we utilized, Numpy we utilized, huge expansive abilities with those two, and TensorFlow. And most importantly, keep an open mind. There is a enormous need for people who know Python in the physical science departments, whether you're doing atmospheric science, any type of geology, ocean science, like we were just looking at. Astronomy is huge right now with machine learning in particular. So Python is also, I mentioned before, a great way to boost your resume and boost how you look to future pursuers and principal investigators, whether you do it at UCSD or in grad school and beyond. And I just hope that you take from this, not necessarily that is, but that it's a great insight into how Python can help you to analyze these intricate problems and kind of a way to approach them that is beneficial and not just difficult and erroneous and tedious, but something that can actually really flow and can actually benefit you into the future. So with that, I'm going to end a bit early, and I thank my guests for being here. I really appreciate it, and I wish that all of you the best of luck in your future, and I hope that you take on Pandas and Python and Numpy and all these different abilities that come with the language into your future, and come to understand the beauty of it as I have. So thanks again, Peter, Sebastian, Eric, you guys are great.